here's our question. So the question says that a plane flies at an airspeed of 120 meters per second. So just to dissect this and terminology, but also just to be frank with all of you, we're never going to do the problems like this after this unit. These problems with, we're going to see boats on the water and planes in the air and stuff like that, they are just constructed for this purpose of teaching you how to add vectors together. We'll add vectors in the future, but there'll be things like force and momentum, and they're not going to be planes and stuff like that. This is to teach you how to deal with vectors. Does that make sense? That's how the whole unit is constructed. So although we shroud it in terms like relative velocity and stuff like that, this is not the point. The point is that when we learn how to do force, you understand how to take vectors and break them into parts and put them back together. That's what the point of this is. Does everybody understand that? Okay, I need you to understand that you're not, although your next test will have silly little problems like this, that's not the point of the test. The point is to know if you can add vectors together. So words like airspeed, they seem important now. They're not particularly important over the course of our unit or over the course of the year. But airspeed is how fast the plane is going relative to the air. Okay, so it thinks it's going that fast. But that's not its speed compared to the ground because the wind is blowing. So it's moving relative to the air, but the air is also moving. Does that make sense? So there are two vectors here that we're going to add up, and the sum of those vectors is how fast the plane is actually moving relative to the ground. Okay? So with that said, I'm going to extract the vectors from this, and I want you to be able to do so too, because ultimately this is kind of a pattern of what we're going to do. We're going to identify the vectors, write them in polar, convert them to rectangular, add them up, and then convert them back to polar. That's our math way of doing it. So eventually I want you to do that. But for today, for this moment, we're going to do this graphically, just to see what's actually happening, okay? So I have two vectors, and I think you guys can see them too. There's the plane, which is traveling at 120 meters per second at a heading of 30 degrees north of west. I'm taking the information from the problem, extracting it, and writing it in vector form. And then there's the wind, which is 30 meters per second, but it's just due north, so all I have to write is north. We're going to add vectors together graphically, which means we're going to try and draw them accurately. But I can't draw a vector that's 120 units long. So we'll have to come up with a scale, because this is going to be a scale image of the actual thing. I conveniently made sure that the two lengths of those vectors are proportional. Do you notice that the plane is 4 times faster than the wind? So you're going to need to construct two vectors, one of length 4 units and one of length 1 unit. Does that make sense? So you could make 1 unit a centimeter or an inch, or 1 unit could be 2 centimeters. Then the plane would be 8 centimeters. You'll need to choose a size that is reasonable for you to deal with. Based on the size of my screen and my protractor, I actually chose inches. It works out. So I'm going to do mine all in inches, okay? But you should choose one that's convenient for you. I think centimeters has some advantages, and that each centimeter has 10 divisions, and not something crazy like 1 over something 32nd inches, if you take my meaning. Inches are broke up weird. So let's start by drawing a reasonable place to do this. And what I mean by that is I want to create something that I can use to demonstrate the origin. So I'm going to create a coordinate system. I would highly encourage, even for the mathematical parts of this, that you always create something like this to use every time you're going to do one of these problems to help you with reference. So that's what I'm going to do. Every time we do one of these, I'm going to start by having a coordinate system. And in my head, I know that east and positive, north and positive, west and negative, south and negative. The negatives and positives are arbitrary choices. It doesn't have to be negative and positive like that. I'm just going to do it that way for consistency's sake, okay? All right, now here's where we have to learn how to use our protractor. I want to draw a vector that is 120 units long, or 4 units long, at an angle of 30 degrees north of west. So this protractor has the hole in the middle, so I'm putting a hole on the origin. I'm putting the baseline so that it is lined up with the horizontal axis, and I'm marking where 30 is, right there. So now I want to draw a vector that is an appropriate length. So you have to choose this for yourself. I'm going to draw one that's 4 inches long because it works out on my screen here. So I place my protractor in such a way that I can draw a 4-inch long line. Is that what you guys got? I hope. Something like this. Now, unfortunately, all the stuff I drew is all in the way. So let's just get it over there so it's not in the way anymore. I think that was a sneeze, so we'll go with bless you. All right. Good so far. Any problem with this? All right, well, the next job is we want to add the next vector to it. Now, this part's important. When we add vectors together, they're like a set of instructions. We go in order. So I've done the first vector, which told me to basically go out, 4 units at 30 degrees north of west. My next instruction says to go due north 1 unit long. So I want to draw another vector, but I want to draw it with this being the new origin, because I'm starting from there. Imagine it's like a treasure hunt where you have a series of instructions that keeps telling you to go. Well, you follow one instruction, and then after you find that spot, it says go to this next place. Well, you start from where you just left off. So we're going to do that. And so to do that, I think we need reference. Now, this one is not particularly complicated since we're just going due north. But in the future, when it's another angle, you may want to just draw in some reference, and be careful. You want your reference to be as accurate as possible. Now, we're just going north on this one, so this one's not hard, but I'm trying to prepare you for the future. Although once we do the math of this, you may never want to do it this way again. So I'm going to bring it down a little ways. And here we go. My next one is, I don't really need the protractor for this, because it's just 1 unit long and it's due north. But I'm going to use a ruler, and I'm going to try and make it as accurate as I can, because we're going to take measurements from this, and I want to compare it to the actual calculated amount. All right. So I've carefully drawn the second vector, and I made sure to make it 1/4 as long as the planes vector. Everybody good so far? All right, the next part's easy. Take your ruler and draw in the result. The result is a vector that starts at the origin and ends at the top of the last vector. So I'm going to draw in a straight line. Make it as straight as I can. Starts from there and goes to there. So the white arrow is the plane's airspeed. The green arrow is the wind, but the yellow arrow is the resultant. The word resultant just means the sum of the other vectors. We good so far? Now, we're doing this graphically, which meant we've been doing this to scale as much as possible. So now we want to start getting some scale measurements out of this, because the yellow line is actually what the plane does relative to the ground. It's important to realize the plane actually faces this way the whole time. So it's pointed in one direction, but is moving in another, because the wind keeps pushing it off course. So we're going to watch videos tomorrow of planes in high wind, and you'll see this. And if you've ever landed here at Tampa when it's been high wind, you've probably felt it because the plane has to come down at an angle, and then once the back wheels touch, they have to turn the nose and then bring it down. It can be a little unsettling. Luckily for us, Tampa has a variety of runways it can use. There are some airports that have less flexibility, and they can be very abrupt. So let's see what we're going to do next. We have to measure the angle, and we have to measure the length. So this is where we're going to use our protractor skills again. So again, mine is right at 41 degrees. Now I also have to measure that length, and that's going to be a little harder, but I'm going to be trying to be super careful to measure the length. Mine is 4 and 5/8. So my resultant length is 4 5/8 inches. All right. So I just took the measurements right off of mine. Are you guys good? Yeah.
How did you find the resultant?
What do you mean, the length of the resultant?
Yeah.
I just measured the length of it with my ruler. So I measured I put the ruler here, measured from here to here to get its length. Now, did you choose a specific length for the plane, the one from here to here? Okay, so keep that one in mind. You're going to need it in a minute. Okay, is everybody right here where I am? We're all good? I want to find the I want to write the answer to this problem. We're just adding these vectors together. We did it graphically, but I need to put it now in meters per second. So this part might not have occurred to you, but this is how you use a scale. You created a scale. My scale was 120 meters per second stood for, 4 inches stood for 120 meters per second. That's my scale. My vector for my plane was 4 inches long, but it was supposed to represent 120 meters per second. So my scale is a fraction. I'm going to set that equal to the plane speed in meters per second divided by what I measured, 4 5/8 inches. So 120 is to 4 as my unknown speed is to 4 5/8. Does that make sense? Well, I need a handy dandy calculator now so I can do the calculating stuff. All right, it's a big do as I say, don't do as I do. I'll have to use my phone. Keep giving my calculator to kids. So 120 divided by 4 times 4 5/8. There. I get 139 meters per second. I got 138.75. I don't know what you guys get. You're probably getting something around there. It's not going to be the same because A, your scale was different, and B, you measured probably a little different than I measured. Go ahead.
So everybody's going to get a different answer?
It should be close to this. But yeah, I think everybody's going to measure a little different. That's the problem with doing it graphically. Now, we're just about done. My actual airspeed is 139 meters per second. And my angle, 41 degrees north of west. Go ahead.
For the proportions, is the 4 inches like the original one you measured, and then the 4.58 what you got after?
Yeah, the 4 inches is this length. Because that's where I set the scale. I said I'm going to make the planes 120 equal to 4. And I did that because the wind was, 4 times the wind was the plane. Does that make sense?
Yeah.
So yes, I created that part of my scale. And then I measured this as a result, and I'm trying to figure out if this one is 120, how long is this one? That's what I'm trying to get. Does that make sense?
Yeah.
Okay. Now, I assume all of you have some version of this or something close. This number may be off a little bit, really depends on how you did your measurements. This number may be off a little bit, depends on how you did your measurements, but we should be all in the same ballpark. This is solving the problem graphically. And there are some advantages to doing it this way. We're gonna do this mathematically now, okay? And it's a 3-step process, but each one of these steps has little things that you have to do inside each process, but we should get the same answer, or really close to it. So let's start with our plane, 120 meters per second at an angle of 30 degrees north of west, and our wind, which is 30 meters per second due north. Step 1. And my step 1 might be a little different. I think you should make yourself a chart. The thing is, if you make yourself a chart, it will help you have a place to hang all of your information. And some of you need me to help organize you. So I made a simple chart, something that goes through these steps. You start with your vectors here, you convert them here, you add them here, and you convert them back. That's our 3 steps. So my chart is designed to help me hang all the things where I need them to go. But I'm still going to have to work this out a little at a time. Now my first step is to convert all my vectors from polar to rectangular. I'm just going to do the wind right now. The wind is pointed due north. I don't think I have to do a whole lot of fancy work because it's going to be 0 in the x direction and 30 in the y direction. That's the wind, right? It's going just up. So I don't have to worry about doing anything fancy about breaking it up into parts because 100% of the wind is in the y direction and none of it's in the x direction. All good? Yet the plane's going to be a little pesky, so let's get something to which we can work. I'm going to put myself a little bit of graph here on the side so that I have something to hang my information on. I want to convert the plane from polar to rectangular, so I am making up something that I can use to hold my information, something graphical to help me work the problem out. Because step 1, although it just says convert them all to rectangular, you know that's a more involved process. And it starts with wrapping a triangle around your angle. So I have set up my angle. I'm going to wrap a triangle around my angle. Does this all sound familiar from yesterday? So I'm going to draw a couple of arrows here. I always draw my arrow that's next to the angle first along a cardinal direction because it makes it better for you if you do. And I'm going to stop when I'm directly below the arrow because I want to draw a right angle so that the right angle is always on my cardinal direction. Cardinal directions are north, south, east, and west. So I'm going to immediately go straight up there, and I'm going to hard write in this right angle to remind me that these are component vectors. They individually make up the vector I'm trying to replicate. So this is 2 vectors that make up our 3rd vector. So we have something that is in the x direction and something that's in the y direction. Those 2 component vectors represent the plane's velocity. But it's also telling me how much of the plane's velocity is to the west and how much of the plane's velocity is to the north. Now that I've wrapped my triangle, I can just do the triangle thing, right? Opposite, adjacent. This is the part that's going to take you the longest, but the truth is, you've got to get that down to like 30 seconds. That's practice. So do it now, please. You practice. So these are our 2 parts of our triangle. We have found the 2 sides. Now that we have the sides, we can write this as a vector equation. I want to be very careful here when we write this vector equation, we have to take positive and negative into account. So this is minus 103.9 in the x direction, because it goes to the left, and plus 60 in the y direction, because it goes up. Again, we have to write a vector equation to complete our rectangular part. But now that we've done that, we have finished step one. Yay, we converted all of our vectors to rectangular. Now, the easiest part, we just add. So just add straight down, right? All the y's should be lined up and all the x's should be lined up. So when I add straight down, I get minus 103.9 x hat plus 90 y hat. So I added the vectors. That part's easy. Any question about that? Now, this is the plane's velocity relative to the ground, but it's expressed as a rectangular, and we have to express it as a polar. So we need to take this and convert back to polar. Okay? So I'm going to ignore what's here, and I'm going to try this again, giving myself some reference so I can work this part out. We're doing kind of the opposite of what we just did. So I'm going to follow these instructions to construct my answer. It says to go 103.9 to the left. Right? 103.9 in the negative x direction. So I've drawn something that represents 103.9. And then it says to go 90 upwards. Okay, I've gone 90 upwards. These are my two component vectors. They are at a right angle to each other, and they express the velocity of the plane, which is this result and this angle. Right, we created a triangle. The difference is this time we had the sides of the triangle and we had to draw in the hypotenuse. It's the only difference from what we did yesterday. So we had the sides, we drew in the hypotenuse. But do you notice? We have two sides and we're looking for the hypotenuse and an angle. Have at it. You know how to do this. I'd probably use Pythagoras. It's easier. So 103.9 squared plus 90 squared equals r squared. I'm going to use Pythagoras. You guys see where I'm going? I'm also looking closely and recognizing that I need the angle. And I have the opposite side and the adjacent side. There's probably a trig function there that'll work. Thinking tangent of theta equals 90 divided by 103.9. I'm not trying to give it all away. I'm just saying these are the kinds of things I'm expecting of you now. We learned how to do the trig. You know Pythagorean theorem. This is what I got. I did the inverse tangent of 90 divided by 103.9. I got 40.9. And then I did Pythagorean theorem to get r. So my answer is 137 meters per second at an angle of 41 degrees north of west. I'd say that agrees with our little experiment, didn't it? The graphical one, doing it by hand, is reasonable, but this is the answer.